Welcome back to my YouTube channel. Today we discuss the important question, that is use of standard deviation information. So far we have working with a desirable non-continuous probability distribution, one where a random variable like return can take only certain values within an interval. In such cases, we do not have to calculate the standard deviation in order to determine the probability of specific outcomes. To determine the probability of the actual return in our example being less than 0, we look at this shattered section of the table 5.1 and see that the probability is 0.05 plus 0.10 is equal to 15%. The procedure is slightly more complex when we deal with continuous distributions, one where a random variable can take on any value within an interval, and for common stock return, a continuous distribution is a more realistic assumption, as any number of possible outcomes ranging from a large loss of a large gain are possible. Assume that we are facing a normal, continuous probability distribution of returns. It is symmetrical and well-shaped, and 68% of the distribution falls within one standard deviation, right or left. Of the expected returns, 95% fall within two standard deviations, and over 99% fall within their standard deviations. By expressing difference from the expected returns in terms of standard deviations, we are able to determine the probability that the actual return will be greater or less than any particular amount. We can illustrate this process with a numerical example. Suppose that our returns distribution has been approximately normal with an expected returns equal to 9% and a standard deviation of 8.38%. Let's say that we wish to find the probability that the actual future return will be less than 0. We first determine how many standard deviations. 0% is from the means 9%. To do this, we take the difference between these two values, which happens to be 9%, and we divided it by the standard deviations. In this case, the result is 0.09 and 0.0838 is equal to minus 1.07 standard deviations. That negative sign reminds us that we are looking to the left of the man. In general, we can make use of the formulas where R is the return range limit of the interest, and where the z-score tell us how many standard deviation or is from the mean. Table B in the appendix and at the back of the book can be used to determine the proportion of the area under the normal curve, that is z standard deviation to the left or the right of the mean. These proportions corresponds to the probability that the one returns outcome would be 7 standard deviation away from the mean. Turning to appendix table B, we find that there is approximately a 14% probability that the actual future return will be 0 or less. The probability distribution is illustrated in figure 5.1. The spreadsheet area is located 1.07 standard deviations left of the mean, and as indicated, this area represents approximately 14% of the total distribution. As we have just seen, a return distribution standard deviations return out to be a rather versatile risk measure. It can serve as an absolute measure of returns variability. The higher the standard deviation, the greater the uncertainty concerning the actual outcome. In addition, we can use it to determine the likelihood that an actual outcome will be greater or less than a particular amount. However, there are those who suggest that our concern should be with downside risk occurrence less than expected. Rather than miss variability both above and below the mean, the people have a good point, but as long as the return distribution is relatively symmetric, a mirror image above and below the mean, standard deviation still works. The greater the standard deviation, the greater the possibility for large is disappointments.